Hello everyone again, and in this part of the presentation, I just want to go over the system layer parts of the ASTRA-sim. So the system layer, as I described before, basically tries to capture the system level aspects of distributed training platforms, such as the communication libraries and also how to schedule the communications. And if someone is interested in more detailed modeling of the systems, for example, the interference between memory reads and sending data out to the network. Those details also could be captured here in the system layer. Actually, one of our papers in ISCA 2021 studied that interactions as well. So the system layer, basically, in a high-level overview, in the ASTRA-sim subfolder, which contains all of the source codes, there is another subfolder called system, and then in the system, the main file of the system layer is the sys.cc, and then you have another subfolder called collective communications, and also the topology that are virtual topologies that are used by the system layer to run these collective communication algorithms. Now, what do I mean by virtual or logical topology? So the thing is that each communication algorithm needs to create and work based on a logical topology. So for example, you may have all these GPUs physically connected through a switch, a single switch, but you may want to run a ring-based algorithm. So that's why you logically create a ring, and then the ring algorithm works on top of this ring logical topology. And then we have the logical topologies here, and the collective algorithms are in system / collective. So this is just a small typo here. So these two subfolders are the most important subfolders here. And collective algorithms, basically here, I want to explain how collective algorithms work. So here, basically one can define new collective communication algorithms using simple state machines, the way that it is currently also implemented. So let's see what do I mean by these state machines? So on the left is the example that Tushar showed in the previous slides, and on the right is the identical state machine that one can use to actually express this algorithm, this ring-based algorithm. So for example, here you can start with the init condition of the state machine, and then on the first step you transition here to the wait for receive, but before transition you also send some data to your neighbor and also receive some data for the other neighbor. And then after that, after you received, you just reduce your the data that you just received from with the data that locally you have, and then you'll iterate and loop through these states. So the next step again is identical to the previous state. So you just send some message, you just receive some message. Once you receive the message, you reduce the message, and once the message is reduced with your local data, again you start this process. So this process continues until you get, excuse me, let me connect my laptop to the charger. Yep. So here, once you finish the reduce scatter phase, basically what happens is now you go and transition to the states that are corresponding to the all-gather phase of that. So, and all-gather is even more simpler than the reduce scatter. So you just transition to a state to just send the data and then wait for receiving the data. The moment that you receive the data again, you you store it and also send the data to your right neighbor to propagate the messages for the altogether. And in the last step, once it is done, you just transition to the state machine, the state of done, and after this, your collective algorithm is finished. So here is the end of the altogether, which actually marks the end of the all reduce as well. So this is how simple one can capture these algorithms through the state machines in the and define new types of collective communication algorithms in ASTRA-sim. And the class of collective communication actually is an abstract class where just it has just a handful of functions that one needs to override, and the main one is the run function, which basically inside that you implement this state machine, and that the rest is taken care of by ASTRA-sim too, and also you need to then introduce it to the other to the part that ASTRA-sim is invoking and instantiating those new interfaces in the system sys.cc main file. So basically, just implement of that abstract class, and then in the system.cc, there's a place where these new collectives are being instantiated. So there it needs to be added as a new class as well inside that sys.cc code. So one of the main jobs of system layer is also scheduling these communications in a way that actually all of the links that you may have are utilized. So you get the maximum link bandwidth utilization. So here, suppose that you have a, let's say, 3D torus again on right. And so you have 3 dimensions. You have the rows, you have the columns, and also you have the local dimension that here you have. So because you have physically 3 different dimensions, you want to schedule communications on all of these 3 dimensions at the same time. So ASTRA-sim, what it does is that it creates 3 different queues. And suppose that you have an big all reduce here. So ASTRA-sim has this knob to break this all reduce into a smaller ones. And then start by scheduling all of these all reduces in the first queue. And here the all reduce, if you look at the state-of-the-art way of executing the all reduce, they start by hierarchically executing the all reduce. So you want to first do the reduce scalar locally, and reduce scalar across the rows, and then reduce scalar across the columns, and do the all gather in a reverse order. So basically, the first stage of these all reduces are reduce scalar and on your local dimension. So ASTRA-sim breaks it into a smaller reduce scalars and run these reduce scalars independent of each other. So the first chunk of the all reduce, which is now doing reduce scalar for the first dimension, here the moment that it finishes, it goes to the second dimension. So now the second dimension corresponds to the rows here. So this means that at this point in the simulation, both the rows and also the local dimension are being utilized for different chunks of the data. And the moment that they go here, now the second chunk goes to the dimension 2, and the first chunk goes to dimension 3. And now the third chunk goes here in dimension 1. So at this point, the full pipeline is filled entirely, and this means that at this point, both the local dimension and excuse me, let me use the laser pointer. Both the local dimension, the rows, and the columns are so the rows and the columns are all utilized at the same time. So ASTRA-sim does this pipelining and chunking automatically. So there are some knobs in the system layer input to make sure that the maximum link bandwidth utilization is achieved. And we are following the state-of-the-art way of scheduling the collectives that proposed in collective communication libraries. So these chunks, the moment that they finish their reduce, scatter, and all gather phases, then they retire. And once all of these chunks are done, then the entire big all reduce is done, and then the system layer can inform the workload layer that the communication is finished. So then the workload can proceed with further operations. Now, I want to talk a little bit of this inputs that one has access to in the system layer. One of the inputs is this scheduling. So this is a sample system layer input that can be fed to ASTRA-sim. And one of the knobs is the scheduling policy LIFO versus FIFO. Basically, this means that through the training, this real training, we might issue multiple collective communication operations. And we might be interested that give higher priority to the communications that are most recently being issued by the workload layer. If it is the case, then we use the LIFO policy. Otherwise, if you want to give priority based on the order in which they receive, we just give them FIFO. So this endpoint delay is basically tries to capture some of the compute and congestion aspects of the endpoints when a new message is being sent. So before each message is being sent, we might need to add some delay to just account for these bus transactions between, for example, the GPU and the NIC itself. So one can add these delays here to account for those transactions. And here, active time period dimension is based on my previous slides. You have multiple dimensions, and you for each dimension you have a queue. But you might say that, okay, I want to run more than one chunk per each queue. And here you can define the order of concurrency for within each network dimension that you might have. And here it's this option is basically telling that if you get an R reduced by the workload layer, how many splits you want, how do you want to divide that big R reduced into, and you want to break it into how many splits. And here when it is set to 4 means that if I get an R reduce of, let's say, 4 MB by the workload layer, the ASTRA-sim breaks into 4 1 MB chunks and run these chunks independently so that it can pipeline these chunks to utilize all of those network dimensions at the same time. And this one is some option that for the text-based engine, you can set it to want to boost some of the simulation speed while might or might not sacrifice latency. So you can see more information in the GitHub page as well. And then here, maybe it's one of the most important aspects that you can define different algorithms for different collective communication algorithms. For different collective communication patterns. For example, if you have an R-reduce pattern, how do you want to run it for this experiment and on top of that target platform? And here we are assuming that we are designing this system input for 3D torus, for example. And what I want to do is that I want to run this R-reduce in a phase-based manner, 3-phase-based manner, because I have a 3D torus, I have 3 dimensions. So I want to run them using 3 phases. And in each phase here, I'm just describing the type of algorithm that I want to use for that dimension. Because I'm tuning this system layer for a 3D torus, and each dimension of the torus is a ring, basically, I want to use ring-based R-reduce for each dimension of that 3D torus. And a similar thing for all gather and reduce scatter and all to also. Here, because our topology was very simple, then the algorithms are also very simple or identical across all these different patterns. But there is no obligation that these implementations should be identical, and you can use any type of algorithm that is supported by ASTRA-sim here to just tell the system layer how to execute these collective communication patterns. And this one is, this pattern is basically saying that do you want to do execute a all reduce in a sense that it should be reduce scatters all the way from first dimension to the last dimension, and then do the all gather in a reverse order in a bandwidth efficient manner, or you just don't want to do this and you want to do just all reduce in the first dimension, all reduce in the second dimension, and all reduce in the third dimension. So you don't want to break it into reduce scatter and all gather phases. These are some of the first way that I mentioned is the bandwidth efficiency is actually proposed in the state-of-the-art methods and recent papers that it is better, but we provide this option that one can use for an alter between the bandwidth efficiency and more simpler version of executing the all reduce in this case. And please refer to the GitHub for more information, and we constantly update those docs and explanation there, and also we answer to the issues raised by the users there. And at the end, I just want to show you that there are opportunities for further optimization of the system level aspects. And one aspect that we targeted and is published in the last ISCA was optimizing the communication scheduling for hybrid network backends. And basically the method we used was called TEMIS, and also we also developed new ways of prioritizing the chunks within a network dimension. So these two options are added and is currently in the main ASTRA-sim repository. One can also add these configurations there and then see how TEMIS can improve the performance of the communication on hybrid networks. And using that, I want to say that all these ideas of how to optimize the system level aspects such as communication schedulings or or coming up with new collective communication algorithms basically can be captured through the system layer of ASTRA-sim, and users can implement their ideas and also add new configurations here in the system layer inputs to test their ideas. Yeah, with that, I will finish my part on the